Hey guys, what's going on? So what you're watching here is a clipped video from a whole video that you'll be able to access if you become a member on Patreon or if you become a member on my YouTube channel. These videos are relatively difficult to make because I'm using multiple sources to compile all the information together. And so with your contribution, I'll be able to make more content as well as create exclusive content for those of you who are really invested into this channel, who really want to understand a lot of advanced physics and life sciences. So with that being said, make sure to hit the like and subscribe button. Make sure to go onto the Patreon page and you can contribute there. You can also become a member here on YouTube. So let's now get into the topic. Hey guys, what's going on? So today we're continuing with stochastic field theory, and we're going to go over a little bit of temperature because the concept of temperature not only is important in thermodynamics, but it's also important when we're talking about probability, statistics, and stochastic field theory. So with that being said, make sure to hit that like and subscribe button. Make sure to go on to my Patreon page or become a member of this channel if you want to support the channel and get exclusive content as well. Again, when you watch these, you're watching only part of it. If you want to get the full video on many of these for many of these videos that I produce, then you can go ahead and become a member on Patreon and so forth. So with that being said, let's get into the topic. So we're talking about temperature today. Today we're going to talk about some more of technicalities behind temperature, what it is exactly in terms of entropy, and then we're going to get to it what it is exactly in terms of biophysics, because I think we often sort of, when I first started going into the concept of temperature, it was I learned the equations, I learned the physics, I learned the entropy and the enthalpy and all this kind of stuff, but I felt like I didn't really fully acknowledge exactly what it physically was until I got into this realm of biophysics. And so we're going to go talk a little bit about that as well, what it means to sense temperature from our perspective, and then we're going to get back into the physics in later videos. So let's recall some things about probability distributions first. So in order to make sense of statistical field theory, we're going to need to talk about the concept of temperature, and to do this, let's consider these the following probability distributions. So these probability distributions, so we have one here where we have a two-coin system, okay? And in our two-coin system, we have these potential outcomes. Coin 1 is tails, coin 2 is heads. Coin 1 is heads, coin 2 is tails, and coin 1 is tails, and coin 2 is tails. And then we actually have heads as well, which is what I have right here. But we want to put some physics into this now, right? So suppose, for a quick second here, that we only have access to these three states, okay? And we need some more energy to access another state, okay? So one way of thinking about this is perhaps through I'll decrease the size of my thickness really quick. But we could think of this as like a potential energy well that might look like this, for example, okay? And so we have energy here, and then we have some reaction coordinate at the x-axis, or time, right? Or we have time, and over time we need to get some certain amount of energy to access another state. That might be a weird way of thinking about it, but really what I'm trying to depict here is that initially we only have access to be able to achieve three of these states. We need a little bit more energy to kick into the system to achieve the other state, which is a head state. Now what we're going to do here is we're going to label these states. These are the relative energies that we apply to each one of these states. And also I've talked about applying numbers to each state and then finding exactly what the average is for these numbers, or the expectation value, if you want to call it that. Suppose for these two, right, these are degenerate, right, so they're going to have the same value attached to them. So let's just attach some arbitrary number 3 to this one. So it's going to be, we're going to have 3 joules, say, for this one, and then 1 for this one. So this one's a very low energy configuration, or very low state configuration. The entropy here is going, so we have 3 possible states. The entropy here is the log of 3, which is this. The expectation value for the labels is going to be 1.75, because that's at 3 plus 3 plus 3 divided by, or 3 plus 3 plus 1 divided by a total, which is 3. We're going to get 1.75. And then suppose over time we add some energy to the system. So we add some energy to our system. Doesn't really matter what the form of energy it is. It could be light energy, it could be heat energy, it can be some form of energy, kinetic, potential, whatever. But we add enough energy to the system now to where we can now access another state. And so that state being a heads-head state. Now what we have is the entropy now increases, right? Because now we have the log of 4. We have 4 potential outcomes. And our expectation value also increases. Okay? So we can calculate and measure the change in the average value of the label, or our energy, over time, and the value of S over time as well. With this, we can calculate the change in S with respect